This is the Monday and Tuesday before the break, and this video is Chem26CBlake. We're going to include that Monday and Tuesday on week 2-6. So this video will go here, and the next one if there's another, which I think there will be, but okay, and we're doing stuff from the end of the chapter review. If we go here to the class, daily plans, second 9 weeks, week 2-6. What I did was, if you weren't here in class to hear the explanation, the next thing coming up is molecular geometries, and this is a good natural stopping point. So we are going to chop this chapter in half right here. And these review questions from the end of the chapter review, which range between number 78 and 105 on pages 274 and 275, they go over stuff we've already learned, and we'll just end the chapter, we'll end this half of the chapter here. Pick up with molecular geometry after the break. So yeah, I need these things done and turned in, but I'm going to go over them here. If you are green, you're catching up with this video for Monday. If you're gold, we've already been over a good portion of this in class. Okay. There is another way, by the way, to name things that I'm going to get into on this video. It's using oxidation numbers. Another way to name more covalent compounds, molecular compounds. Okay, so we're stopping here and taking a break. Number 78. What is the octet rule and how is it used in covalent bonding? Basically, your atoms or your molecules, most of them, and most of the atoms involved in the molecules, other than hydrogen, are going to try to end up with access to 8 valence electrons, and they will share to do that. Since these aren't give and take, ionic was chapter 7. So atoms lose, gain, or share electrons to achieve an octet. Covalent bonding occurs when atoms share electrons to achieve an octet. 79, describe the formation of a covalent bond. Basically, you're going to share electrons, valence electrons. The nucleus of one atom is attracting electrons of the other atom, and they're going to share one or more pairs of electrons, so they both have access to 8. Number 80, describe bonding in molecules. Again, shared electron pairs. Molecules bond covalently by sharing electron pairs. So when you use the word molecule, you are referring to a covalent compound. Describe the forces, both attractive and repulsive, that occur as 2 atoms move closer together. So there's a couple things going on here. One is, if you kind of back up to the previous question, you know, this nucleus is going to attract those electrons some. This nucleus is going to attract these electrons. And there's repulsions between the nuclei and the electrons happening also. But what this question is talking about was this diagram, which your book does one for fluorine. Basically, if you start with 2 atoms that are really far apart and they come closer together, they're going to reach some optimal energy if they're going to covalently bond, where they are energetically more stable. And then if you try to put them too close together, then energy gets really high. So that's what that question is about. As the atoms approach, the net force of attraction increases. At a certain optimal distance between the atoms, the net attractive force is maximized. That was the bottom end of the graph. Actually, the most energy had been given off. If the atoms move closer than the optimal distance, repulsive force exceeds attractive force. 82. How could you predict the presence of a sigma or pi bond in a molecule? Okay, a single I'm going to show you the diagram for this where I went over it. Single covalent bond has only a sigma bond. A double covalent bond has a sigma and a pi bond. And a triple covalent bond has a sigma and 2 pi bonds. So going back here, we went past this a little bit farther. Here is water, oxygen, hydrogen, hydrogen, a couple of lone pairs. Ammonia, methane. But in all of these, you have a bond between a central atom and a hydrogen. And that is one single shared pair between s orbital and a p orbital in this case. That is a sigma bond. A pi bond can happens when you have double and triple bonds. Here I have ethene, hydrogen, hydrogen, carbon, carbon, hydrogen, hydrogen. And between the carbon and carbon, I have a sigma bond. But the p orbitals, somewhere I don't know where it's at in the notes, but here it is. I took this out of the organic chemistry textbook. There's p orbital above and below, another p orbital above and below, and those electrons could be, anywhere in there, top or bottom. They're going to form a bond together on the top and the bottom, and that's called a p bond. It's a single bond. So you have in a double bond, you have a sigma bond and a pi bond. In a triple bond, well, let me do this again. In a double bond, here's your ethene again, single bond and a pi bond. I said single bond and a double bond, and I think I meant to say sigma bond and pi bond. You have a sigma bond and a pi bond. Top and bottom is one bond. So showing it here, we have a sigma bond and a pi bond, and superimposed on one another, the sigma bond and the pi bond. In a triple bond, if you're going to bond these two orbitals, you have a sigma bond there, and you can't see it on here, and a pi bond, top and bottom, and another pi bond in and out of the board. Okay, so triple bond is a sigma bond and 2 pi bonds. 83. Give the number of valence electrons in nitrogen, arsenic, bromine, and selenium. Well, there's a table for this. Last year I gave it to you. This year I'm not going to. You just have to use a periodic table. But I'm going to pull up from last year. I've been using it. Well, it's here. It's here. Okay, so I guess I put it as my screenshot since I was using it so much, and then I forgot about it. Okay, so we have nitrogen, which is in this family. It has 5 valence electrons. By the way, it's going to share 3 in our chapter here. Arsenic is below phosphorus, which is below nitrogen. Also has 5 valence electrons, will also share 3, typically. Bromine. It's in the halogens, it's about here. It's got 7 valence electrons. They can share more often, they're going to take electrons, but they can share. Selenium, that's below sulfur, which is below oxygen. So it's here, it's going to have 6 valence electrons. It's going to share 2 more. Okay. Okay, the sigma bond, 84, we already kind of talked about this. Locate the sigma bonds and the pi bonds in each of the molecules. That's formic acid, I think. Where am I at? Locate the sigma and pi bonds in each of the molecules below. Okay, in the first one, you've got a double bond, that's a sigma and a pi. The bonds between the hydrogen and carbon are sigma bonds. In B, the triple bond, you got sigma bonds on either end, but the triple bond has a sigma and two pi bonds. You probably already know that. 85, in the molecules CO, CO2, and CH2O, you have CH2O right above there in A. Which CO bond is the shortest? It's the one with the triple bond. Okay, so it's this one, carbon monoxide. And it is the strongest. Consider the carbon-nitrogen bonds shown below. 86. It says which bond is shorter and stronger? It's the triple bond in the cyanide ion. 89. When is a molecular compound named as an acid? If one of the hydrogen atoms is ionizable, it could come off of there. So when it releases hydrogen ions in solution. As an example, as a dry gas, HCl is called hydrogen chloride. If you bubble that into water, the vast majority of this will ionize, produce hydrogen ions, and then it's hydrochloric acid. Next one, 92, complete the table, the formula and the name. Okay. So HClO2, I think I had a mistake on one of these there the other day and they caught it. HClO2 should be chlorous acid. H3PO4 is phosphoric acid. H2SE is hydroselenic acid. HClO3 is chloric acid. Name each molecule. 93. Oh, here's what I want to do. That's not in this chapter. It is in this book way in the back, and this is normally in its chemistry course. This would be where you would introduce oxidation numbers, and we kind of need it. So I'm going to talk about it here. There are two naming systems. The naming system you learned in this book, the old names were nitrogen trifluoride, nitrogen monoxide, sulfur trioxide, silicon tetrafluoride. And I added some more. Two more, nitrogen dioxide and dinitrogen tetroxide. There is a stock system name. The old naming system is not acceptable unless you have to use it. And there are times when you have to use it. Or if you're talking about gases, for some stupid reason, we usually use the old naming system. What you're supposed to use in chemistry is the stock system name, which uses oxidation numbers. So we may not even get to it this year. We didn't get to it last year, so I threw it in with this chapter. Fortunately, we had access to it. For nitrogen trifluoride, that's NF3. What you're doing is you're saying, I know this is not charges I'm about to write, they're oxidation numbers. They're written above, and the charge goes, or the sign goes first. Fluorine is -1. Because this is a neutral compound, these numbers must add to 0, and we got -1, -1, -1, and something goes in there to make all that equal 0. What goes in there? A +3. So this compound is nitrogen 3-fluoride. That's the acceptable name. This one is an old name. It's not really acceptable. Nitrogen trifluoride, believe it or not. Let's do this one. We'll do sulfur 6-oxide. Which is sulfur trioxide. which is SO3. Now how do I know fluorine is -1? Fluorine's always -1. There are some rules called the oxidation number rules. These are on page 686, table 2. You should take a look at it. And there are rules. There's one in here for fluorine. Fluorine is -1, always. It's the king of the elements. Oxygen is usually -2. Rule 5, the oxidation number of oxygen in compounds is always -2, except in peroxides and some other stuff. And this is not an exception. So oxidation number is, and this is a neutral compound, so this has to add to 0. -2, -2, -2, oxygen's oxidation number is -2. The charges I'd write 2 minus, oxidation number is written -2. So what must this one sulfur be for this to add up to 0? +6, -2, -2, -2 is 0. So sulfur's oxidation number is +6. That's why its name is sulfur Vi and Roman numerals 6 oxide. Now let's try nitrogen dioxide and nitrogen tetroxide. Nitrogen dioxide is NO2 and dinitrogen tetroxide is N2O4. Now for NO2, they have to add to 0. For dinitrogen tetroxide, they have to add to 0. I have 2 oxygens, they're -2 apiece. What? -2 -2 gives you 0. +4. So this first compound is called nitrogen 4 oxide. What about the next one? I have 4 oxygen, they're -2 apiece. I already showed you do that rule in the oxidation number rules, it said so. -2, -2, -2, -2. Make sure there's 4 of them. And something has to add to 0. For our class, we'll make sure our somethings are always the same. It wouldn't have to be, but that's weird. So we're going to make sure it's already the same. What and what? -2, -2, -2, -2 gives you 0. +4. And the name of this compound is also nitrogen 4 oxide. Now you can see why, even though we're supposed to use the stock system name all the time, there are instances like this where it doesn't work. And you have to use the old naming system so you know which compound you have, because NO2 and N2O4 are not the same thing. So they can't have the same name. Now, you might say, well, then this one's better. No, because there's reasons why this one is not better. And this one, so which one should we, well look, nature doesn't care that we have this naming problem. Nature does what nature does, and it's our problem that we want to classify everything. So there is not one way to do this that works all the time. So we actually have 4 naming systems, 2 for ionic, 2 for molecular covalent. On ionic, you have binaries and names for stuff with polyatomic ions. You should know both of those from last chapter. In this chapter, we have the old naming system and a stock system naming system. You should be good with both of them, although this is the one that we're testing over in this chapter. Okay, next question. Okay, name each molecule. Okay, apparently this is 93 over again. I'm going to cut the video there and go to another one.